Question 1. Give the simplest ionic equation for this reaction. It's going to be S2O32 minus plus 2H plus, and we form SO2 plus S plus H2O. So the property that causes pollution that enters rivers: acidity, and the reaction of SO2 to water, SO2 plus H2O plus water to form H2SO3. That's it. 1.3. Draw a diagram to show the shape of the molecule of H2O. We've got the oxygen, and we have the two hydrogens, and we've also got two lone pairs of electrons. State the bond angle: 1/4.5 degrees. Explain the shape and bond angle. Well, lone pairs repel more than bonding pairs. Therefore, bond angle reduced. And originally probably be 105 degrees, so it reduced less than 109.5 degrees, and 4 marks to that. Question for 1.4. Describe an experiment. Sodium sulfate and HCl. I really like this practical, so it's just going to be pretty nice for me. One method. We want to use disappearing cross. Put acid into container with cross, add second reactant, and start timing. You know, these practicals are just memorizing it and all the key details and even the minor details that they can test you for markers on. And the best way to do it is just review them constantly. Maybe one practical a day. For 30 days you've gone through 30 practicals. 30, you know, and there's only, I don't think there's more than 10. Maybe there is, maybe 15. So then you know, it's just about repetition. Repeat at different temperatures, obviously, and record time for cross to disappear. And obviously we want to control ensuring the variables, the cross, the volumes and concentrations of solutions kept constant. Obviously apart from temperature, that's the thing we're changing. Then stage 3, use of results. Well, 1/T is a measure of rate. Plot of rate against T, and then sketch. It should look something like, you know, this, where that's temperature, that's rate, bracket 1/T. Should look something like that. Obviously not as steep, but something like that. Question 2. Draw a displayed formula of molecule H2SO4. S double bond O, double bond O, OH, OH, H2SO4. Given equation, so each stage in dissolution of sulfuric acid equals solution. So we've got H2SO4, and then obviously we get HSO4 minus plus H plus, and then we've got HSO4 minus reversible reaction SO4 2 minus plus H plus. Describe the method to make this solution. Classic question, 4 marks. Weigh the solid and transfer using a method that allows an exact mass to be known. 2 weighings, one could be zeroing and method by difference. When they dissolve in water in suitable container, not in 250 centimeters cubed water, transfer into washings into 250 centimeters cubed volumetric / graduated flask, and then make up to mark, which is 250 centimeters cubed, and the final step, invert / shake. State the units of Ka. Okay, this is a bit of a calculation question. 6 marks. It does not look easy. Okay. Well, Ka is equal to H plus A minus over HA. Well, the square brackets represents the concentration, so in this case the concentration H plus, and in this case concentration A minus, in this case concentration HA. I can find out the concentration of H plus. That's very easy using this simple formula. Concentration H plus equals 10 to the power minus pH, 10 to the power minus 1.72. And we want to find out the calculated value of Ka, hydrogen sulfate ion. We know we've got the mass of this, of that, in that much. So we need the concentration, so I can find out the moles, and then I can find out the concentration, and then I can, okay, yeah, you know what, maybe it isn't that hard. It actually is very simple now that I look at it, just a lot of steps. Then I can find out the moles of obviously NaHSO4, but I need to convert the milligrams, that's the trick. So it's going to be 0.605 divided by the MR, which it doesn't give us, but the MR is 120.1, 5.04 times by 10 to the power minus 3. And now obviously we want the concentration of the NaHSO4, so moles concentration, volume concentration is moles divided by the volume in moles per dm minus cube, 100 times by 10 to the power minus 3. Actually, that is that, and then the initial of NaHSO4 is equal to HSO4 minus, we need to times by 10. So I get 10 by 10 to the power minus 2. And Ka, we can say is equal to, yeah, obviously that, but we can also say Ka is equal to H plus squared, and in this case divided by the HA, HSO4 minus. Then substitute the values in. We've got 10 to the power minus 1.72 as constant HA, so it's just going to be that squared divided by what's the change in concentration, so 0.0504 minus 0.0191 of the H plus ions, and you should get 1.17 times by 10 to the power minus 2, and the units mole per dm minus cubed. Think about it, we've got squared divided by itself, so it's going to be mole to the power 2 dm. I know forget about that. It's going to be mod per dm minus cube squared over mod per dm minus cube. So that cancels out, and you're just left with mod per dm minus cube. Explain why this increases the pH of a solution when sodium thiosulfate is dissolved in a sample of solution question 2.4. Well, the equilibrium moves to the left as sodium sulfate is added to counteract, to remove the increase SO4 2 minus. Therefore, so H plus, so concentration of H plus ions, well, what's going to happen now? Well, that's going to decrease, hence pH increases. Remember, as pH and H plus are the opposite. If H plus increases, pH decreases. If H plus decreases, pH increases, because pH equals minus log 10. And I can't do the square brackets. Well, hopefully you get the point of H plus. Name the piece of apparatus labeled A. Or, you know, practical is a salt bridge. And the purpose of in this case, the salt bridge, just to complete the circuit. The substance used as electrode B in figure 1, platinum. Yep, platinum. Complete table 1 to identify C, D, and E from figure 1. Include the essential conditions for each 4 marks. So the conditions should be pretty straightforward, but identifying C, D, and E. C, D, and E. Well, C, you can clearly see here. D is what we put in here, and E is what we're getting out. C is HCl. D is obviously going to be the, because we get bubble, it's going to be the H2, hydrogen. And E is going to be FeCl2. The Cl plus ion bonds to it, so Cl minus ion bonds to it, so FeCl2 and FeCl3, because we've got a 3 plus ion and a 2 plus ion. The conditions, I feel like that's hard, but the conditions you should know: 1 moles per dm minus cubed. H2 hydrogen is a gas, 100 kilopascals pressure, and 1 mole per dm minus cubed. So those are concentrations. You don't have to include temperature in this one because it doesn't give us one to that. And then it says we do need the 298 Kelvin. 298 Kelvin. It says any mentions 298 Kelvin. That's the temperature. Give the ionic equation for the overall reaction in the cell. H2 plus 2 Fe3 plus our 2H plus 2 Fe2 plus H2 plus 2 Fe3 plus our 2H plus 2 Fe2 plus. Change to the apparatus to allow the cell reaction to go to completion. Replace the voltmeter with lamp. 0.6 complete table 2 show the missing value from experiment 4. I thought it was just 3 marks for just completing the missing value. I was really confused. So 4 is going to be ln Zn2 plus, so 1.0 divided by 0.010. We should get 2.30. And the graph, obviously, you just plot it against that. Minus 5, minus 4, minus 3, minus 2. Actually, I'm doing it too much, as I should be like minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 0 mark. Should be straight line. Obviously plot this as well, so we also need a line here, 1.004, start at 4. Yeah, minute lowest value is that, and then you just keep going. 1.05, 1.06, 1.07, 1.08, 1.09, and you get the point. You know, you need to fill it in. 1.12, 1.1. Obviously, I've done this pretty incorrect, the scales, but yeah, you should get the point. And then you just plot it, and it should just be a straight line down. It goes through here. Obviously, the points as well. Calculate the gradient. Use a gradient to calculate the temperature. So to calculate the gradient, just calculate the gradient. Minus 0.013, and so it must be negative. You can clearly see it's decreasing. It must be negative gradient. Just pick 2 points. Y2 minus y1 over x2 minus x1. To calculate the temperature, well, the temperature is going to be my gradient divided by 4.3 times by 10 to the power minus 5, and I should get 302 Kelvin slash 303 Kelvin. Give one reason why your calculated value is different from the standard electrode potential. We've got CH2, CH, CN, H, CN, same thing, just repeating units. And obviously show these as well. 5.1 gives the equation for reaction between iron and sulfuric acid. Fe plus H2SO4. FeSO4 plus what's remaining, H2. Calculate the mean titer. Pretty nice. Just add them all up. So, we need the concordant titers. 22.70 plus 22.60 divided by 2. 22.65. Don't add them all up, because that is not concordant. That's more than 0.1 centimeters cubed away from the rest. So you should get 22.65 centimeters cubed. Give the ionic equation for the oxidation of that by mangate ions. So Fe2 plus MnO4 minus AH plus R5Fe 3 plus Mn2 plus 4H12 5Fe2 3 plus Mn2 plus 4H12, and obviously need 5 here. Color change, colorless. At endpoint of the titration, colorless to pink, obviously. A piece of apparatus used for these stages of method, taking the portions, pipettes, and adding the solution, potassium manganate solution, burette, because we can add it drop by drop. And the final question, classic percentage uncertainty one. Now this one says balance used to a